Welcome to today's Science and Christianity class. Um, it is Matter and Quantum Mechanics Part 3. Our verse, Proverbs 16:33, is, "The lot is cast into the lap, but its every decision is from the Lord." And we'll see how that enters into our discussion later. Well, last time we went through the birth of quantum physics. We talked about how Max Planck was able to accurately describe the black body spectrum by applying a math trick he found. He only allowed energy to take on values that were whole multiples of a particular quantum of energy. And it was equal to a constant he came up with, h, which we call Planck's constant, times the frequency, depending on the particular frequency of the electromagnetic light. We also saw that Einstein's analysis of the photoelectric effect found that apparently little particles of energy make up electromagnetic waves, and they happen to have an energy that matches the same condition that Max Planck found in his analysis of black body radiation. We then talked about how the Bohr atom, with its discrete energy levels that came from quantized angular momentum, sort of explained spectra. It explained the hydrogen spectrum really well, and some other atoms pretty well, and then some not very well. But it seemed like a step ahead, a step in the right direction. And then finally, we talked about how de Broglie proposed that particles actually had a wave nature as well, which was quickly confirmed in 1927. That enabled an understanding that the electrons in the Bohr orbitals, well, they turned out to be standing matter waves whose wavelengths just perfectly fit inside of the orbital. So each orbital was a whole number of wavelengths in terms of the de Broglie matter wave. And that seemed like a really amazing thing. Well, with that, we're ready to step ahead, and it's kind of a giant step here. In physics, there are lots of formulas, and another name for a formula is a function. So if you put the values into the formula that you need to calculate with, and then you actually calculate the formula, you get your result. And in physics, these sorts of formulas, which we call functions, they are used for everything. So Schrodinger, a physicist in around 1926, given de Broglie's finding, wanted to come up with a general sort of function that would describe the matter waves for, say, electrons in an atom. He wanted to come up with a function that would describe the matter waves for those electrons, but there was no way just to know out of the blue what such a function would look like. So what he did was he took a step back and he said, okay, I need to come up first of all with some general strategy for obtaining a specific wave function, which he decided to call psi, the Greek letter that looks kind of like a pitchfork. And so he went about trying to come up with a general equation, which he could apply in a specific case, like electrons around an atom, to come up with what the particular matter wave function would look like for those electrons when he applied that function. So he wanted the wave equation for matter waves. Now, that may sound a little confusing, so let's take a step back. Okay, um, and this is just kind of going through what I just said, but with a little more assistance. The way physics usually works is there's some sort of very general equation, okay, a mathematical statement of some sort, very general equation. Um, and so here's basically our equation, the top one there from Newtonian mechanics. It basically says the force is mass times acceleration. In some fancier math, but it's a very general equation. It describes not one kind of motion, it describes any kind of motion whatsoever. And so typically what you do with an equation like this is you tailor it to the specific situation that you're interested in, and then that enables you to find the function, the formula describing the specific thing you're interested in. So here, for example, suppose you throw a ball at a 45-degree angle. Well, you start with that top thing, which describes all motion. You put in the, you tailor it to reflect the specific situation, like throwing a ball at 45-degree angle, and then from that specific equation, you find the formulas that express like the position of the ball given the time t. How long has it been after you've thrown it, and so that is a specific solution to your specific equation that you got from kind of applying the general equation of motion. So that's how physics usually works, no matter what it is. So same thing happens with wave equations, and we're kind of doing a broad class about physics and Christianity. So we briefly touched on the fact that waves are important in sound, and waves have been important in light, and we even talked about Maxwell's equations. But by this point in time, the 1920s, there are lots of wave equations in Newtonian physics that the physicists are quite used to. For example, here's a general wave equation, the one that's kind of highlighted in the very center. This general wave equation describes basically the surface of a membrane, say, on a drum. So basically like the vibrating membrane on a drum, and the kinds of sounds it can make. Or if you happen to sprinkle sound on that and you play sound, how will that membrane vibrate? Well, I've pictured that latter case here. So this thing in the middle is a very generalized wave equation for the kinds of vibrations that can occur on that drum skin. Okay, and then what sorts of actual patterns you could see in the sound as you allow that thing to vibrate in response to sound. What kinds of sound patterns you would see are quite varied, and there are actual YouTube videos you could go look at things of this sort and see that you can get all kinds of different patterns using different kinds of sound. Well, this wave equation in the middle, all those possibilities are in this very general wave equation. But then if you apply specific conditions, like you're going to cause the drum to receive certain sound and vibrate accordingly, then that very general wave equation in the middle, well, then you can come up with a particular wave function that describes what you would then see, right? What kinds of patterns you would see on the surface of the drum skin. And, you would actually be able to get out some sort of function that would basically be the formula that tells you what that pattern looks like. And you could do all kinds of things with that, including create these sorts of images that are on the right. So this is a wave equation that describes sound, or at least the vibrations sound will cause on a drum skin, and then the kinds of patterns we could visually see that would be visible as the drum skin vibrated, because we have sand sprinkled on it, so we could see the little, kind of the little pieces of sand jumping up and down, and that all comes out of the general wave equation. Okay, so we're going to do the same thing in quantum mechanics, and it's a very big part of quantum mechanics, which is why it seems a little abstract. I'm taking the time to explain it. We're going to do the very same thing in quantum mechanics, but what we have to do first is come up with the general equation that happens to be sufficiently general so that all the solutions we're interested in obtaining are hidden in that equation somewhere. Okay, so here's the gist of what Schrodinger did. The way he proceeded was somewhat more sophisticated, but it's equivalent to this. First of all, I'm saying he, but first of all, to go through the kind of similar logic to what he did, that's more understandable. We can start with the core principle of energy conservation that comes out of our study of Newtonian physics. What was that principle? It says that if you add up all the energy, right, all the kinetic energy and all the potential energy, you get the total energy, and that's a conserved value. At least unless you're adding energy to a system, you're taking energy out. As long as you're not adding or taking out energy, and you're looking at, whatever it is, whether it's a ball bouncing on a trampoline or any number of other things, the kinetic energy plus the potential energy, that's the total energy. So the kinetic energy may change over time, the potential energy may change over time, but their sum will stay constant. Okay, now Schrodinger wanted to somehow, or at least to kind of parallel what Schrodinger did, we want to somehow work in something that represents the wave, because we want this to be a wave equation. So we're taking a very known principle in physics, the conservation of energy equation, and we're going to try to turn it into a wave equation. So one really easy way to do it is just to multiply all the terms in our energy conservation equation with something that represents the wave, which we'll use psi, because that's what Schrodinger used historically, and that's what's typically used nowadays to represent particularly the quantum wave equation. So kinetic energy, so if we do that, we get kinetic energy times psi plus potential energy times psi. It must equal the total energy times psi. Okay, so it is a wave equation, but it's not very helpful, because literally anything would work in this equation, right? If you had a situation where you already knew what the kinetic energy was, say as a function of time, you already knew what the potential energy was as a function of time, and you knew what the total energy was. Any attempt at coming up with a wave equation psi, any specific wave equation that you could dream up for psi, any function at all, would work in that equation. Mathematicians say it would work trivially. In other words, because all we did was multiply both sides by psi. So in and of itself, that's not very helpful. But here's what to do. Now we need to bring in de Broglie's ideas about matter waves. Okay, and so from de Broglie's ideas, we can know some things about energy and momentum and wavelength given any particle of matter. So we know what the de Broglie wavelength is, and we know how it relates to the energy and momentum. Okay, and it turns out we can do some math, and we can find that there's a way to rewrite the terms in our previous step. So this kinetic energy times psi in our previous step, and our total energy times psi in our previous step, we can actually come up with substitutions by by kind of working de Broglie's ideas, and that gives us a general wave equation like the one below that appears in that kind of green region there. And we don't have to understand all the symbols, but I just thought I would kind of read it to you. So it's negative h bar squared over 2m, where that m is the mass, and that h bar is Planck's constant divided by 2 pi. Okay, it just is. And then it talks about how the wave function, it's how fast the rate of change of the wave function changes as you go to different positions or different times. Okay, because the wave is not the same height everywhere, like a water wave. It's not the same height everywhere. It has peaks and crests and everything, and it changes over time. Well, the matter wave would have this general equation too. So that the rest of that term by the h bar squared over 2m, that's basically how fast is the rate of change of the wave function, as you change position and time, and then plus the potential energy as a function of position and time times just the wave function. And that's equal to I h bar, we'll talk more about I later, times how fast the wave function is changing over time. All right, that's a bunch of gobbledygook, but I just wanted you to hear it because it kind of should sound kind of like what we're talking about here. Okay, and we're not going to need to understand the math of this. I just thought it was helpful to hear that this equation is nothing other than what it is we're representing it to be. It's a general equation, and if we put in specific conditions into this equation and we turn it into a specific equation, then we solve that, we can determine what the actual wave function is in that particular case. So that's kind of the plan here, and that's what Schrödinger was after. He wanted that general equation. Okay, so what we have to do is, in that general equation, it's got a V, a big V. It looks almost like voltage or something, but sometimes that's used for potential energy, and of course voltage is a type of potential energy. It's potential energy per charge, but here it just means the total potential energy. So to come up with a specific solution, we have to put in what the potential energy is at different places as a function of time. And then if we solve that thing, then we've got our wave function that describes a matter wave, and that's it. Now the math is usually not very easy, okay, but that's how it works. Okay, so the interesting about this equation is, and again, this is math, so you can take my word for it, is mathematicians call this a linear solution. It doesn't look too linear, does it? Does it look like, if any of you remember your algebra from high school, it doesn't resemble kind of the functions that were used to talk about straight lines. Well, it's not talking about straight lines on a graph paper. By linear, what they mean is if you have any two solutions that work, because there may still be multiple solutions hiding in here, even once you put a particular potential in there, you may get multiple solutions out. Any two solutions that work, you can also create yet another solution by adding them together, or subtracting them one from another, or even multiplying either of them by a constant number. And then again, you can multiply both of them by constant number and add them together. All of those would also be valid equations. It's kind of like on a little puddle or something. If you see a ripple, you know, a little wave develop, maybe because just like tap the puddle with your foot. If somebody else taps the puddle on the other side with their foot, well, both the waves you cause and the waves they cause um, are a solution to the wave equation for that puddle, and also the sum of those two things would be a solution, and that corresponds physically to both of you, two people tapping their foot on the puddle and causing a little ripple, and then you get the combined effect of both waves together. Well, this equation allows for that sort of thing, which physicists call a superposition of waves. In other words, when two waves meet, they just kind of add together. Okay, and you get your diffraction patterns and everything out of that. So this is the right kind of equation. It seems to have the right kind of mathematical property. And the other thing is, and this is kind of an interesting thing, it turns out that very often, we can consider situations where the total energy of the system is not changing. Okay? In those situations, we can take the very general, very general wave equation called the time-dependent wave equation, and we can come up with a little bit simpler equation, simpler in terms of figuring out solutions to it, that doesn't involve time. So if you look at the one on the bottom, all the t's have gone away in that one, and we have a new symbol E that means the total energy. So it turns out that if the total energy is fixed of a system, then this bottom equation can be solved, and the solutions in the bottom equation, it turns out that you can just multiply them by a factor and get the general solution that would work in a general solution that would work in the top equation, including time. So if you get a solution at the bottom, which is a small psi, it's kind of like a pitchfork, but not quite as heavy looking as the top one. If you multiply that by this factor involving time, and you see that at the third bullet point, e to the negative iet over h bar, you get a solution for the top equation. And here's what's interesting about this situation. Anytime you've got a situation where the total energy is remaining the same in the system, the solutions to the bottom equation give you all the solutions that are possible to the top. But then here's the fun part. Even if energy is not constant in a system, you can still find all possible solutions to the top equation by having combinations of solutions that are valid when the energy is fixed. So you can still add and subtract enough of these together, these time-independent solutions together. You can still add and subtract enough of them together so that they give you all the solutions, even if the energy is changing, the total energy of the system is changing. So this was Schrodinger's equation. And we kind of started off with the earlier illustration about how sound waves can cause vibration on a drum head, and you can see the patterns in the sand, and we had a wave equation and everything. It turns out a guy named Fourier invented some math that can be applied to lots of things, and often is applied to analyzing sound waves. And the little character up there is basically telling us when Schrödinger came up with this equation, there was a whole rich library of math that could be tapped into by people who were interested in solving that equation and describing real physical situations. And so the math was all ready and waiting for people to seriously use this equation that Schrödinger came up with. it should be mentioned that there was a whole different approach to quantum mechanics that was created by three guys named Heisenberg, Born, and Jordan. And they used a whole different type of mathematics, which most people would probably say is a more elegant, more refined version of mathematics. And it turns out that the quantum mechanics they came up with is equivalent to Schrodinger's wave mechanics. It ends up looking very different. It took a little time for them to see that, but it's interesting. They didn't really focus on the waves. They focused on the quantum jumps that occur between states. So if you think back to the Bohr atom, which is where quantum mechanics happened to be, up until these guys in Schrodinger came up with their different approaches. If you look at the Bohr model of the atom, the whole thing about the Bohr model of the atom was electrons could only jump between allowed orbitals in an atom, and it would either need to absorb or give off the amount of energy that would allow them to move from one energy level to another. They focused on that, and they came up with a very elegant mathematical way to describe how you could apply de Broglie's ideas to matter and come up with solutions. And it turns out it was just another way of doing the same thing. So modern quantum mechanics involves both sets of thinking. Both sorts of math are helpful, and so they all kind of jointly figured out a way to analyze a situation and come up with the matter waves that are physically descriptive of that situation. Okay, what I'm talking about is a very high level, and it doesn't sound. I know it's not very concrete, but hopefully it made some sense. And if not, maybe we'll see as we look at some examples. How it kind of works. It's not easy stuff, quantum mechanics. It's not the kind of thing that people who are majoring in physics in college start with. So don't feel bad if it's a little tricky. And let's see if we can understand it practically. Let's see how it works. Well, we do want to do that, but there's a little hitch. Physics has never quite gone down this sort of path before. Like with Newton, when you started with your general equation of motion, then you came up with, you tailored it for a specific situation, then you tried to find the formulas of motion for whatever it is that you were interested in. There's one hurdle we have to get over before we can take Schrodinger's general wave equation and find the actual wave that happens in a particular case. And it turns out we have to try to understand the meaning of the Schrodinger wave equation just a little bit better. And it's not going to be a very mathematical discussion, it's going to be a very philosophical discussion. Okay, so what does it all mean? Well, first thing to address is that I in the equation. You can see kind of circled down in the green area on the right, there's an I h bar, and the h bar is just Planck's constant divided by 2 pi. That I is not is not a normal thing in earlier sorts of physics. It's called the imaginary square root of -1. So what's a square root? If you have a number 4, we generally say the square root is 2, okay? Because you can take 2, multiply it by 2, and you get 4 back. So 4 is 2 squared. 2 is the square root of 4. We can also say that -2 is the square root of 4. So, because if you multiply a negative times a negative, you get a positive, and -2 times -2 is also equal to 4. So 4 has 2 square roots, 2 and -2. Um, but if I ask you what the square root of -4 is, well, in normal numbers, there are no square roots of -4. It doesn't even make sense because any number is either, any number you multiply by itself is either going to give 0 or a positive number. You can't get negative values. So what mathematicians did actually during like the 14 and 1500s or so, they came up with an interesting way to deal with this kind of situation. They realized that if you could just figure out a square root to -1, then you could do all the math you wanted to do for these otherwise impossible cases. So let's take our -4 example. We don't know, there can't be an answer in what we call the real numbers for the square root of -4, but we could think of -4 as just 4 times -1. Okay, so if we did know what the square root of -1 was, then we could say that the square root of -4 will be the square root of 4 times the square root of -1. Okay, so, you know, 4 has 2 possible square roots, plus and minus 2, but -4 would then have 2 square roots, plus or minus 2 times the square root of -1. Okay. Now, in the real numbers, there is no such number as the square root of -1. So mathematicians defined a whole system of numbers that could have they could have real numbers, but they could also have numbers that were multiples of the square root of -1, whatever that is. They just defined it to be a thing. And those multiples are called imaginary numbers. And if you add a real number together and an imaginary number, you get what mathematicians call a complex number. So you have both a real and an imaginary part in general. Now, when you have a wave equation, right, that has an imaginary, what we call the imaginary unit, that I, which is supposed to be the square root of -1, it's all well and good that mathematicians know how to deal with complex numbers and get, and actually use them to do meaningful things and helpful things. But it's not so obvious what it means when it shows up in a physics equation. And you know what? The equations, like if you take this top equation with the I in it and you come up with a general solution to the Schrodinger equation, an actual description of the matter wave, which means how big the wave is at a certain point, guess what? Mathematically, you're not going to get a solution that just has plain numbers. You're actually going to get a complex number out of it. It's going to have a real part and an imaginary part. So this is a whole new world for physics. This is something that mathematicians have done in the past and made sense out of, and it sounds bonkers, right? But now this physics equation has this same I in it that's supposed to be equal to the square root of -1. It sounds nuts. About quantum mechanics in general. I mean, he said this on an occasion. It may not have been particularly about this, but I think it's fun to bring up a quote Einstein had in response to quantum mechanics. He said that God is subtle, but malicious he is not. So as we wrestle with meaning here in what Schrodinger came up with, it already seems like we're struggling to make rational sense that's physically meaningful. Because in the real world, in nature, things have particular measures. Things are so many feet wide or so many meters long, or, have a certain temperature or certain volume, or, there's a certain amount of energy it takes to do something, right? And those are all real physical values you're talking about. They don't include they don't work with complex numbers where you have some real number plus some multiple of the square root of -1. So at first glance, this is pretty off-putting, and people are still chewing on this today. You might wonder, if it's so weird, why are we even talking about it? Why aren't we just moving on to the thing that eventually takes its place that does make sense? Well, it turns out this is one of the foundational parts of modern physics, and although it's expanded, and we have new wave equations that take into account things that Schrödinger did not take into account. Basically, this is a core part of modern physics, and it's not wrong. It's just really tricky to deal with in a philosophical way, and we're just scratching the surface with the fact that it has the square root of -1 right there in the equation, and that the solutions to this equation will generally be complex values with an imaginary number component. Well, fortunately, Max Born, one of the guys who worked on the alternative version of quantum mechanics to what Schrödinger did, but was pretty much participating in the development of quantum mechanics, he realized that this is not unlike the situation that happens with Maxwell's equations and electromagnetism, which now we know, right? Electromagnetic waves they're waves, yes, but at a tiny level, they're made out of all kinds of little photons. Well, Max Born said, we could interpret the wave function that comes out of this general equation in the same way that we interpret the wave intensity that comes out of Maxwell's equations as just the probability, just in a way that gives us the probability of finding a particle. So in Maxwell's equations, the intensity, which actually has to do with the square of either the electric field or magnetic field, or depending on how you want to look at it. I mean, there are different ways to express it. It has to do with the square. Max Born said maybe if we took the size of the complex number, not the complex number itself, but we took the size, like, if you made a little triangle and the real part was on one axis and the complex part was on another axis, you take the size of it, which is kind of like the hypotenuse. If you take the size of it and square it, maybe that's the probability of finding the matter particle there at that point. And so that was his suggestion. In other words, that's how he took something that had complex numbers, which included an imaginary portion, and he turned that into something that is physically meaningful. And he did it by analogy with Maxwell's wave equations. Well, you know what? And maybe a little surprisingly, because he was working by analogy, there was a little bit of a guess there. It was kind of an informed guess, but that turned out to be the interpretation of making physical sense out of Schrödinger's equation. Using this interpretation, we can employ quantum mechanics to describe physical reality, especially at a very small level. And this interpretation that Max Born suggested has held up along with Schrödinger's equation or quantum mechanics in basically every experiment ever. Einstein's special relativity and later his general relativity, which we haven't talked about yet, but it's strange on its own too. And this quantum mechanics here that we're talking about, as bizarre as it is, those two pillars of modern physics are more tested and more poked and prodded than anything else in the history of science, and all our modern technology is based on those things, and our standard model of physics, which we'll talk about later, is based on those things. It works, but it's bizarre stuff. Okay, so as we said, the fact that you've got that I in there makes psi itself, the wave function itself, I mean, we were able to interpret it kind of in a way that gives us a probability, but as far as the wave function itself, you know, like what size the wave is at a particular point, it's non-physical because it's not only a real number, it's also an imaginary number. But the fact that we're interpreting it the way Max Born suggested, which works, right, as a probability, you know, like we're able to get a probability out of it. That's a real number. Well, now not only is psi itself non-physical, even though we made sense out of it as a probability, but in addition to that, it's what physicists call non-deterministic. Okay, now what does that mean? What does that mean? Everything from the time of Newton on in physics until now has basically been here's the physics, here's how it works. You put in your particulars, and physics tells you how things are going to happen, right? You know, so engineering is built on top of physics. Technology is built on top of physics. And physics was called deterministic because you put in your values into your formulas and you got out specific answers. Okay? Your specifics determined the answers. Quantum mechanics, it's not so. You put in your specific values, and the best you can do is get out probabilities. So physicists call that non-deterministic. And that isn't what they were after. It's not what anyone wanted. It's just what happened when you started dealing with matter waves. Okay? Remember, last time we talked about how very strange it would be to even conceive of a particle of matter being a wave. Well, it turns out when you analyze the situation and come up with a general wave equation describing matter waves, the strangeness gets baked in. Okay, so it's really, really essentially there. In fact, people have kind of proven that you can't escape it. Okay, so I won't go into detail. I mean, at a very fine level, quantum mechanics describes the situation far better than Newtonian physics, but it is very strange stuff. Okay, so other wave functions in physics, and still other sorts of functions beyond waves of any type, they all were derived with the physical meaning in mind. That's how the analysis happened that came up with those general equations in the first place. Schrodinger's equation was not derived that way. Schrodinger said, hey, let's suppose there is a wave function, big psi, let's bake it into these known equations and somehow incorporate de Broglie's work about matter waves and see what equation we get. That's basically what we did. And the thing is, no one to this day knows how to interpret the wave function itself, in terms of what's waving. It's not a thing, but the probabilities that we get out from the Born interpretation, those are very real, and those correspond to reality, and they enable us to do all kinds of things we could never have done before without them. Okay, well, as I said, these are all big issues. We're into the territory of philosophy here. people who study philosophy would say, you know, there are questions here about metaphysics, epistemology, and ontology. In other words, how um, how things work beyond the natural realm, just how they work, you know, at a higher level, metaphysics, or how we know what we know and what can be known, epistemology, and the very nature of existence itself, ontology. Okay, um, you know, so unlike Newtonian physics, our outcomes in quantum mechanics are going to be statistical, not deterministic, um, and basically quantum mechanics is going to be accurate in what it does tell us, but we won't be able to know what will happen in specific cases. We'll know probabilities, okay? And you know, scientists are able to see that those probabilities hold up, but we'll know probabilities. You know, we know that the wave function itself over time changes because t is one of the variables in the general equation, but you only know what a particular measurement is going to be at the moment you measure. Okay, so you might know the probability of getting a certain measurement from quantum mechanics, but you don't know what measurement you will get until you actually measure it. And for one, Einstein felt this was very unsettling and it bothered him a lot. And so he famously said, God does not play dice with the universe. You know, because if it all comes down to probabilities, according to quantum mechanics, Einstein didn't find that very pleasing or attractive. He found it very questionable. Bohr, you know, who continued to be involved in quantum mechanics as it developed, Bohr was a little less bothered by it. He was just happy that you could do calculations that worked. He, according to I guess recorded history, he told Einstein in response, "Stop telling God what to do." So I guess Bohr was saying if God wanted to roll the dice, he could. And we're going to actually have a further perspective on this toward the end of today's class, which I hope we'll all find gratifying, because there's a way to resolve at least some of this in terms of God, you know. But yeah, quantum mechanics is weird, and it has weird implications. Okay, and here's Heisenberg chirping in. He's saying in regard to we can't know something until we measure it. He says, you know, it's not only that, but when we do measure something, we'll know actually less about other things that could also be measured. Okay, so for example, if we take an object, say that's moving, we can measure its location, but the closer we know the position of the object, the less we'll know about its momentum. Newtonian mechanics had no such problem, right? And vice versa. If we try to measure the momentum closely, then we'll be ever more uncertain on the position. And same thing happens with time and energy. There are several relationships of this sort that people refer to together collectively as the uncertainty principle. And it's something that Schrodinger came up with, but it can also be derived from the Schrodinger equation. You can look at the general Schrodinger equation and you can find this uncertainty principle hiding in there in that equation. And so just to be clear, when he says the better you measure position, the less you know momentum, right? It's not a situation where you don't know. It's more like a situation where you can't know. So the better you measure, say, position, the less you can know about momentum, and vice versa. So very, very strange implications. This has long caused a problem in the world of physics. People have wrung their hands about what it all means still. I personally went to graduate school in physics, and left graduate school in physics. I decided physics was not for me because it was so crazy, and it took decades for it to start to grow on me all over again, you know. But you know, because there was no physical reality to the wave function itself. In other words, it wasn't the height of a water wave, or it wasn't the you know, the relative pressure in a sound wave or something measurable. People ask, in what sense does it exist? And Bohr's answer was, you just, it's fundamentally unknowable, but it works. Just use it. And there's a professor, David Merman, who came up with a famous paraphrase. The paraphrase is, shut up and calculate. In other words, he's saying that's what Bohr essentially had to say to everybody. Stop philosophizing, don't worry about it, it works. We derived the thing, it came from principles that work. It's a statement of truth, and the probabilities we get out of it are you know, they tell us how to do things that we otherwise don't know, and it all works. We keep seeing it over and over in the experiment. It keeps predicting new things that are true. Just shut up and calculate. But of course, many find that not very gratifying. Schrodinger himself is one of those people. So, if you can believe it, the very person who came up with the wave equation, the quantum, you know, to describe matter waves, he himself found it completely absurd. Okay, ridiculous. This idea of probabilities, you know, of probabilities being the best you could do. And not only that, but you know, it turned out when you had a wave equation, that until you measured it, you know, all possible outcomes were still possible. So something about the act of measuring forced one of these possibilities to become actual values. Okay, and so he came up with like kind of a metaphor for what it seemed like to him, and the metaphor was his attempt, Schrodinger's attempt, to explain how ridiculous quantum mechanics seemed. So here's his thought experiment. Okay, it turns out that quantum mechanics can even describe, and we'll get to the principle behind it in a little bit. Quantum mechanics can describe the nature of radioactive decay. Okay, so in earlier classes we've talked about radioactive decay, and you know, like with radium or uranium, such things as that. Okay, but here's the thing: no one knows when a particular atom of uranium or radium is actually going to give off an alpha particle, or a gamma ray, or a beta particle. It's just probabilistic. And it turns out quantum mechanics describes that situation just right, and it gets the probabilities right because it knows how fast, you know, if you have a big sample of uranium, like a kilogram of uranium, it knows how fast that the atoms eventually decay on, you know, because it knows the average, and there's zillions of atoms, and so, you know, you can see what it does, and it's consistent. But he said, okay, so let's suppose you have a little tiny sample of something radioactive, and you have a detector, okay, and you put your cat in a box. Okay, you put a cat in a box with the sample and the detector, and you put a poison chemical in the box too. And so if the detector detects radiation being given off by the radioactive sample, then it's going to cause the toxic chemical to be released and kill the cat. Okay? So if there's radioactive decay in the sample during a particular time, the cat will die. If there's no decay, then the chemical will not be released and the cat will remain alive. Okay, now here's the thing. He said, suppose you pick just the right sample size of radioactive element, not too radioactive, I guess, and so that however long you're going to put that cat in the box and leave it subject to this experiment here, there's going to be a 50-50 chance that radiation will be given off during that time. And so there will be a 50-50 chance that the poisonous chemical gets released. And so there will be a 50-50 chance that the cat dies. Or, equivalently, a 50-50 chance the cat is alive. Now, here's the thing that quantum mechanics says. It says until you look in the box and you see the cat, you don't know which it is. And by the way, looking in the box means any way at all of sensing what's going on in that box, whether it's through a little webcam you put in there, or you listen into the box to see if you could hear breathing, or any form of looking in the box counts. Okay. Schrödinger said that quantum mechanics would claim, as understood, this was only a few years after he came up with the equation, but as people were understanding it, he said quantum mechanics would say that the cat is in a superposition of states. One state where the cat is alive and one state where the cat is dead. And until you look, both states are possible. And until you look, it really is undetermined. That's what quantum mechanics would say. And to Schrödinger, that seems so ridiculous that he entirely got out of quantum mechanics, or at least stepped well away from it. So he started pursuing other studies. He was a very academic person, and he ended up focusing on other things to study. So to him, this was just absurd. Well, then there's the question of what constitutes a measurement. We talked about, in reference to the thought experiment Schrödinger had, that any sort of looking in the box will constitute a measurement. And Heisenberg put it this way. He said, or he would put it this way. He would say, whenever you measure something, whenever you look at something, at that point, all the different possibilities that are allowed by the wave function for your particular case, all those possibilities collapse to a sharp peak of just what you've seen or measured. Okay, and how sharp is the peak? Well, it depends on the precision of your measurement. So if your measurement is very sharp, then the peak would be very sharp. If your way of measuring something, whether it's a size or temperature or whatever it is, if it's not very precise, then the wave function will still allow for a narrow range of possibilities within the accuracy of your instrument. That's what Heisenberg would say. Okay, but in no way does it violate the understanding of Schrödinger's cat, as that thought experiment is often called. If you remember back to last time when the two-slit experiment was done for electrons, right? Which is what confirmed de Broglie's idea about particles also having a wave nature. The same thing happened when we tried to measure which electron, or which of the two slits an electron went through. When we measured it, we no longer saw a diffraction pattern that allowed for the entire range of possibilities that were there when the electron could have been passing through either slit. So once you knew which slit an electron was passing through, then it kind of collapsed the wave function, and the diffraction pattern of the possibilities didn't happen. And so when after a lot of electrons, you looked at the overall pattern, because you need lots of these events to see what the probabilities really were of the electron hitting one particular place on the screen. When you in effect measure the electron passing through a slit, you no longer get the probabilities as before. Yeah, just like that. So when you measure something, the wave function collapses. That's what Heisenberg said. But you know, we don't see evidence of these superpositions in everyday life. I guess because as soon as we see something, it's resolved. Okay, but I think there's still a question here. What really constitutes a measurement? Let's say we go back to Schrodinger's cat, okay? And let's say Schrodinger is running this experiment, with the cat in the box, but also he has a friend there. He actually did have a friend named Wigner, or there's a guy who worked in quantum mechanics named Wigner. Let's say he has a friend there. Let's say Schrodinger, right, looks in the box to know whether the cat is alive or dead, but he doesn't tell Wigner. Okay, now from Wigner's point of view, is Schrodinger in a superposition of knowing the cat is alive and knowing the cat is dead, and the cat's in a superposition of being alive and dead because Wigner himself has not measured the result, nor has he been told the result. So to him, not only is the wave equation describing the cat uncertain, but the wave equation describing Schrodinger, who's looked in the box, is uncertain because either Schrodinger now knows the cat is alive or Schrodinger now knows the cat is dead, but Wigner doesn't know which it is. Okay, so we have this subjective dependence on who's calculating the wave function for these things, So it's really very, very confusing, right? People have philosophized that what really causes a measurement to happen is some conscious awareness. Okay, this almost sounds new agey. I wouldn't mention it because I'm trying to stay with things that are solidly held in physics. But this guy here, John Archibald Wheeler, was one of the major physicists in the United States in the 20th century, and this was his way of trying to grapple. He thought consciousness was the necessary ingredient to constitute a measurement, okay? And he even went so far as to say that it's not real until it's observed, okay? No phenomenon is a real phenomenon until it is an observed phenomenon. And he even went further, and he had a notion that the universe itself only existed because it was seen, okay? And he described the universe as like a U. He talks about a universe that developed early on, and it's a small universe. And so if you think in terms of a big bang, and of course no one in nature is there to see the universe at the beginning. But as the universe goes on in bronze, and eventually you have consciousness that's able to look at the universe and even see the light coming from back in time. And so he even argued that in some ways the universe came to exist because later someone in the universe would see back toward the beginning. Okay, which sounds pretty out there. Okay, but I'm just kind of saying it because people have really wrestled with what a measurement really is in quantum mechanics, what really causes the collapse of the wave function, and he thought it was consciousness. Well, for people in the class, we have a demonstration at this point to illustrate how quantum mechanics works, but I'm just going to continue on past that. And you know, as we talk through our material, the same ideas will be covered. It's just we won't have a physical demonstration here. Okay, well, there was a whole different approach to quantum mechanics. Um, Not a different equation, not a different wave equation, not um, not a um, different way of thinking in terms of probabilities, although there was a different interpretation there. Um, um, a physicist named Hugh Everett, came up with what he called the many worlds interpretation. Okay, now he argued that the wave function didn't collapse, that all the possibilities remained going forward. And I'm going to try to explain this. It's very tricky, but this is actually becoming a more and more popular view among practicing physicists. Okay, so what Everett would say, for example, in the Schrodinger cat experiment, he would say that both possibilities go forward, and in one branch the cat is alive, in the other branch of possibilities the cat is dead. And in each branch the observer will observe whatever that branch is. Okay, and you could apply that to Wigner, you know, and kind of the additional twist that we gave it, you know, same kind of thing. In each, you know, so you could kind of look at it as a case of possibilities would just multiply. Okay, so it's called many worlds because each and every branch is like a different version of reality. Um, but Wigner, what he argued, and by the way, just like you can describe a particle in quantum mechanics, you can describe anything in quantum mechanics. You can take two particles and come up with a combined wave function that describes them both. You can take a complex object with many particles and describe, you know, come up with a wave function for that complex object. So what he's really saying is the possibilities all just roll forward and they're still there in the wave function, but then you know, it's like all of them are happening, and all of them are kind of perceived by us in that branch as being our reality. So we perceive that the wave function has collapsed and only left the possibilities open to us. But there are other branches where another version of us would see a you know, the other set. So like in one branch we'd see the cat alive, in the other set we'd see the cat dead. In one branch we'd see Schrodinger saying that the cat was alive if we were Wigner. In the other branch we would hear Schrodinger saying no, the cat died. You know, so it's like this sounds very philosophical. It sounds kind of nuts, and it sounds way out there, but it is very consistent with all of quantum mechanics. So rather, you know, he's saying relative to the reality we perceive we're in, it's like probabilities, but in fact, it just talks about what portion of all the possible realities we're in. You know, like are we in? Is our reality? Is our branch of reality 50% of the realities out there where the cat is alive? Or, you know, because the probabilities are different. Maybe if we're in the branch where the cat died and it was only a 25% chance the cat was dying, maybe that would only constitute 25% of the realities out there, you know. But he says they're all still out there, and that's why it's called a many worlds interpretation. But I will share with the class that that quantum mechanics for over 100 years has not been able to come up with a really good answer for the measurement problem. And the Hugh Everett's many worlds interpretation works just as well as any other attempt. In fact, maybe it works better because it says there is no measurement problem. Quantum mechanics just rolls forward with all the possibilities. And, you know, it's kind of persuasive on a logical level, and I think that's why more and more people are kind of buying into it, which is interesting. We'll return to this later in the course. Here's a really nice picture indicating, you know, what he's saying. If you can imagine an old film reel, you know, where you have all the different frames making up a film, and let's say we're filming this experiment, Schrodinger's cat. He's saying with the many worlds interpretation, it's almost like every time you come to a decision point, the film splits off. Okay, so maybe it starts off with a certain thickness, and maybe, like, let's say in the experiment, instead of the 50-50 chance the cat would die, maybe it was 25-75. He would say, well, you know, like 25% of the film will split off one way with that possibility, and the other 75% would split off the other way, having that possibility. You know, it sounds crazy, but this is at least a philosophical interpretation of quantum mechanics that doesn't have a lingering problem that is called the measurement problem. Well, there's another school of thought, and by the way, these some of these ideas are kind of mutually exclusive, and some of them can kind of play with each other, they can overlap. But there's a way of looking at quantum mechanics that says, quantum mechanics is probabilistic, it's not deterministic. It's not because things are down to probability, and you know, it's not determined until you measure what actually happened. Maybe it's our knowledge is incomplete. So in other words, what quantum mechanics says has held up in experiment after experiment. It's as well tested as anything ever in the modern world. But maybe there's just something we don't know. And it's the something we don't know that would actually allow us to say what the outcome would be. And it would put us back in the same position we would be in with the earlier physics, what we now call classical physics, which included Newtonian mechanics and Maxwell's equations and all that stuff. If we knew the stuff that was missing from quantum mechanics, then we would know what the outcomes would be. It would be something that could be calculated. If we knew what the original circumstances were, we would be able to apply our equations, our full knowledge, and understand what the outcome would be. People who study quantum mechanics call this kind of thinking access. They describe it this way. They say, you know, they call knowing things that are hidden. They call the things that are hidden variables. So theories that talk about quantum mechanics this way, they're called hidden variables theories. In other words, they claim that there are things that, if known, would be predictive, and it's just that we don't know them. Okay, so those hidden variables are out there. They exist. That's what some people would say. And if we knew them, we could determine outcomes. We wouldn't have to resort to probabilities. Okay, so in particular, this guy named Bohm, he actually picked up on something that de Broglie himself started to do with quantum mechanics, and he just took it further. He actually claims another kind of wave called a pilot wave, and the pilot wave is what determines the choices when they're made. Okay, and you know, so it's consistent with quantum mechanics, except it has the extra. Okay, well, the unfortunate thing about it is, okay, because we don't know what the pilot wave would say, We don't know the things the pilot wave knows. Even if it's out there, we couldn't tell the difference between there being a pilot wave or not. So there's no way to test it. All the predictions are just the same as if it's totally a matter of probability. So, in science, when you've got something extra that doesn't add anything, um, it doesn't seem, it typically isn't something that's needed for an explanation. Although quantum mechanics without it is pretty weird. It violates a principle called Occam's razor, which means it doesn't, it's an extra thing that doesn't change what you see. Um, Another name for that is the principle of parsimony. In science, to be parsimonious is to use as few things as possible for an explanation, and so here we have an extra thing, and yet we can't do any better than quantum mechanics without it. So it just doesn't seem to be good science, or at least it doesn't it's not typical of what is considered good science. But then there's a last thing that most people have a big problem with, which it also abandons something called locality. Okay, now in physics, for a long time, there has been the assumption that what happens in a particular place and a particular time depends on things in the vicinity, immediate vicinity of what's happening. Okay? So, in other words, like the sun may have generated energy 93 million miles away that caused plants to grow, right? That I'm eating right now in my body, which caused me to have enough energy to turn on a light switch and the light comes on. But in that moment, all that matters is I have that energy and I'm able to turn on the light switch. The fact that it's only because I ate, and I ate only because the plant grew, and the plant grew only because the sun was shining 93 million miles away, that doesn't change that. The fact is that all you need to do to account for the fact that the light turns on when I flip the switch is to look at what is in the vicinity of the light and the light switch, and that's me, and I have enough energy to flip the switch, and apparently a mind that's able to decide to flip the switch. That's all you need. You don't need to suppose that there's something on the other side of the solar system in that same moment that is somehow exercising some control over where I flip the switch or not. So the thing about this pilot wave theory is it abandons locality. It does not explain all the results of quantum mechanics unless it also abandons locality and starts assuming that things that are widely separated have an impact on each other in a way that would violate our understanding of relativity or causality, or it's just so it's problematic. Now but on the other hand, it's what a lot of physicists would like to believe, that maybe they're just hidden variables, because it's very unsatisfying that quantum mechanics can do no better than probabilities. Well, at this point, maybe um, maybe it would be good to do a sanity check. Just kind of look at the situation and say, is this adding up? Okay, because as I said earlier, Schrodinger, uh, Schrodinger's equation, nor quantum mechanics, is, it's not limited to just electrons in atoms or particles, that are too tiny to see. It really does apply to cats and baseballs and cars and people, but surely, you know, based on everyday experience, they can't really be governed or described mathematically by all this quantum weirdness, can they? Okay. Well, the answer of physics to that is, and this is true mathematically, as you look at bigger and bigger objects that, you know, that especially once they get large enough for us to sense in any way, and we typically call those things not microscopic but macroscopic, but even once they get big enough to see under a microscope, right? It's like, you know, the quantum weirdness has kind of canceled itself out mathematically. It's kind of averaged itself out into things that are sane. Okay, so while quantum mechanics might give you a probability for whether a particular atom of radium will decay or not, when you're talking about a sizable sample, even a microgram of radium is a huge number of atoms, the probabilities work out to be extremely accurate. Okay, so the correspondence principle is that as we leave behind the atomic and molecular worlds and get to larger and larger systems with more and more atoms and molecules, you start seeing essentially the same things that Newton's physics predicts. And that's true. Okay, so one water molecule is weird and quantum. And by the way, you know, a lot of this stuff has been studied, and there are a lot of overall properties of water that kind of would seem to rest on quantum mechanics and have no classical explanation whatsoever. So one water molecule is weird and quantum. But if you have a glass holding trillions of water molecules, the water is well behaved and familiar, and what happens is pretty much what Newtonian physics says will happen. Okay, it turns out that the correspondence principle pretty much prevents us from ever directly perceiving the quantum weirdness. And that's true if you calculate it out. I mean, it's not just a thing they say to try to have people believe the unbelievable. It's a true thing. If you follow the math and work it all out, you see that when you get to, you know, things that are humanly meaningful, the weirdness kind of goes away mathematically, except for certain extreme cases. And the picture on the left is not, it's kind of artistic. It's not how any of these things would actually look. But there is something called Bose-Einstein condensate, which means even if you take a very large number of atoms, if you cool them down to near absolute zero, which we can do, very, very cold, they can actually kind of all start behaving, you know, in a coordinated fashion like one quantum wave. So it's like the whole system of these atoms would start to behave like one quantum wave, and you can start to see really strange behaviors in a macroscopic way, like in terms of you know, angular momentum. Like you can see actually, you know, you can have all kinds of strangeness that occurs, and you get detectable, observable things that some people call like superfluidity. You know, you can see things happening in a frictionless way. You can have superconductivity. You can see current flowing without any resistance whatsoever. And everyone who's ever taken an MRI, you know, has benefited from the fact that you have this extreme magnet that is only possible because of this superconducting wire. So there is some evidence that's kind of human scale that conforms to quantum mechanics and the weirdness in quantum mechanics that just wouldn't be predicted by Newton's classical physics, but it's mainly the stuff in the very small realm that is weird in a quantum way, and the weirdness works itself out. So thing is, though, all the properties that we do see of water, there's no explanation for how water has the familiar properties it has, other than looking at each one of those water molecules as if they're subject to the laws of quantum mechanics. None that we know, and quantum mechanics explains it all very well. So, really interesting, but lots of thinking has to be done when you come to quantum mechanics. Oh, it looks like Jordan there is asking if anybody's seen the cat lately. And he's asking, did the poor thing decohere? Well, we ran the experiment before on the cat, 50-50 outcome, alive or dead. So we thought the cat was in superposition because no one looked in the box yet. But I almost hesitate to say real life, but with all the research going on with quantum computers and that kind of thing, in at least real science these days, when the wave function collapses and it no longer has a quantum superposition of possibilities, they say that it decoheres. In other words, it's no longer benefiting from multiple possibilities. So Jordan says, has anybody seen the cat lately? Did the poor thing decohere? I think he means, did the poor thing die? Oh, it looks like the neighbor's cat is very unhappy. Maybe that cat was its friend. Well, we should move on. I don't think we're going to see the earlier cat anytime today. Okay, so we wanted to see what this crazy stuff did practically because it was very conceptual, but then we had to get all philosophical about the meaning before we even got started. Now I guess we can say, okay, now we've grappled with the meaning, let's kick some tires and go for a test drive. Let's see what we can actually do with this stuff. Okay, so I want again, we're not going to have to worry too much about the math, but I wanted to show you the first example everyone, I think, who's ever taken a class in quantum mechanics hits as their first example. It's called an infinite square well. You know that potential thing that you had to specify in the general Schrodinger equation, like how much potential energy you have as a function of position and time. In this example, the idea is you have infinite potential if you're anywhere except between 0 and L on this little number line over on the left. So this is a one-dimensional case. We're not thinking even in 3 dimensions. We're supposing you're in 1 dimension. You just got a number line. You're somewhere on the number line, and you need infinite energy to be outside the 0 to L, because if anywhere there, you just have endless potential energy. So it's kind of a mathematical abstraction, and inside the range from 0 to L, you have 0 potential energy. So mathematically, you can actually put this into the wave equation to try to come out with solutions, and you get solutions. And what you end up finding out is something a little strange. Like if you imagine putting like a marble on a ruler, right? That's L long, and then it's got walls on either side that keep it from going any further than the ruler in either direction. Well, you might think the ball can have 0 energy on the ruler, or it might have a little motion either way, and you might think that it could have any amount of motion. Quantum mechanics says no, that the actual energy a marble could have inside on a ruler in that situation that would actually have certain energy levels that would be possible. And that's what comes out of quantum mechanics. And it would actually even predict that depending on the energy level that you were at, it would have to be one of them, that you would have different probabilities of being someplace on the ruler or not. Okay. Now these energy levels are very, very, very close together. Okay, but it's not continuous, so you can't just have any old energy level. Okay, so so that's what you would get in this case. Um, Now, usually the second case you run into in a quantum mechanics class is called the finite square. Well, in other words, between 0 and L, you don't have any potential energy. You can have kinetic energy, but you don't have any potential. But if you are on either side of that ruler that goes from 0 to L, if you're on either side of it, you have some potential energy. In other words, by virtue of being in a field that could pull on you, you have some potential energy. How much do you have? Well, whatever this V with a subscript 0, we call that V naught. Whatever V naught says, you have that much potential energy. So if you solve quantum mechanics for this, you also get specific energy levels, but eventually your energy levels allow you to, you have energy levels that are less than the potential you'll have on either side of the ruler, and then you have energy levels that are greater than the potential energy you would have if you're on the outside. And so the ones that are inside would be called like bound states, and the ones that are outside would be called free states because they're not confined to this region. They have enough energy to move around. Once again, the probabilities would be, depending on your actual energy, would not necessarily be evenly distributed across the ruler. But here's what's really strange, right? If you kind of look at this n equals 1, n equals 2, n equals 3 thing, these are like energy, the first 3 energy levels. The wave function that corresponds to the first 3 energy levels of this solution here. If you look, and this wave kind of, if you square the size of it, you get the probability of finding whatever it is, at a particular location. So if you look at these waves, see, before the entire wave was contained between 0 and L. Now you can see that there's some possibility that your item will be outside the range 0 to L, even if you don't have V naught of energy. Okay, which in classical physics, that would seem to be impossible. Okay, but if you measure the location of your item that has, let's say, less than V naught of energy, there is some chance that you would actually come up with an answer that says, okay, the object is currently at -1, or it's at L plus a half, or whatever, when you just don't have enough energy to be there, because then your potential energy would automatically be more than the total energy that you have. And classically that doesn't make sense, but it happens in quantum mechanics. Now, let's do yet another variation on this. Let's say that you have a potential function that you can stick in your wave equation where between 0 and A you have a certain amount of potential that's not 0, and it's in this one it's called V naught, but your potential is 0 everywhere else. Okay, so you put a marble or an electron or whatever it is on the left of that little potential there, on the left side, at some position less than 0, and you solve Schrodinger's equation. What you'll find is you'll get solutions that will have a greater amplitude on the left than the right, but they will still have some amplitude on the right. They won't be 0. I know it's weird stuff, but I'm going to tell you what it means. It means that and let me give you an example. Okay, let's say I'll have a 2-dimensional example. Let's say you have a paint can and you put the marble in a paint can. Okay. the marble could have a little bit of speed and it could roll around the bottom of the paint can, right? If it had a lot of speed, it might even be able to jump out of the paint can, but it would have to have at least enough kinetic energy to get high enough in the can to make it out. In other words, it would have to have at least enough kinetic energy so that it could trade that for potential energy, because right, in physics we have conservation of energy, and get to at least the height of the can. Otherwise, that marble is trapped there. What quantum mechanics is actually no. There's a chance that the marble will just pass right through the wall and it will be on the other side of the paint can. In other words, it didn't have enough energy to go over, but it will actually, there's just a possibility it will go through. Actually, not even that it will go through, that it will just appear on the other side. Okay? This is called quantum tunneling. I'm reminded in the Bible where after the resurrection of Christ, he simply appeared in the room where his disciples were holed up. I mean, this is pretty amazing stuff. Now, the probability of this happening with you or me or a baseball or a marble is so unlikely. It might as well be zero. It'd be like winning the lottery every second for 10 years. I mean, it's that small a possibility for a person to be able to walk through a wall or something, let's say. But if you have an electron and you're in you have a little voltage potential that's kind of keeping the electron trapped, but on the other side of the potential, the electron has enough energy to be there. Every now and then, the electron can leak out, and that's called tunneling. And it's kind of a big deal. So it's at the heart of a lot of electronics, right? Our modern cell phones for sure. The earlier transistors I don't think use this phenomenon, but now there are things called tunneling electron diodes and things in circuits that actually use this to work. And so, your modern cell phones would not work without this happening. There are these electron microscopes. There are different kinds of those, but one of the types wouldn't work without that. Anything that uses flash memory, including your phone, but also like the little things you can stick in a computer, they don't work without this thing happening. Even the sun itself will not shine without this basic kind of behavior happening as described in quantum mechanics. We're going to get to it more, but basically when it comes to things in the atom, the strong force is so strong that it would, well, actually, forget the strong force. I mean, you couldn't have atoms coming together to fuse, and we're going to talk about that more on a different day. You couldn't have that happening if this tunneling would not occur. So this seems like kind of an academic exercise, but it's actually a very big deal. Okay, now that we've looked at some of those cases, what happens if you apply quantum mechanics to an atom? Okay, so there's a way to do that. There's a way to describe this central charge, this positive charge in the middle, this proton. We know that the Coulomb force, the electrical force, is inverse square. There's a way to describe mathematically what it is, and then to ask if you put an electron, if you subject an electron to that electrical potential, then what would be the possible states of that electron? If you solve the general Schrodinger equation, right? If you solve it for that potential, you get actual answers out for where the electron is going to be, at least in terms of probability. And so what you get is that the probable location of the electron at any point in time is going to be subject to this like cloud, because it's three-dimensional now, this cloud of possibilities, and that's going to kind of correspond to the charge density of the electron. Okay, in other words, it's kind of like the charge of the electron is kind of spread out, but it's kind of like a standing wave, not unlike, when we saw that the de Broglie wave applied to the Bohr model would give us the idea that his electrons were actually standing waves around his nucleus. That still happens in the Schrodinger equation. You get these standing waves, but they're kind of waves of probability. Actually, the wave function itself has to be kind of similar to squared in order to get these probabilities. But the actual probabilities that you get, they kind of make these different patterns in space, and it's not like a simple two-dimensional pattern. It's not like a simple circle that corresponds to an orbit where the electron's somewhere on there. No, it's three-dimensional in space, and so all those things on the left are some of those solutions, and um, they're kind of the flat view. It's kind of like a cross section of it, but you get some pretty exotic patterns out of there, and from everything we can tell, they really do exist. Okay, so you can solve these things. Here's a more vivid picture that shows what the solutions are for a hydrogen atom with one electron. Okay, um, and of course, all these different things correspond to different possible energy levels, and not every possible energy level, or not every possible energy, is allowed to exist as if you're an electron in a hydrogen atom. Only certain energies are allowed to exist, and if you get too much energy, then you can leave the hydrogen atom, and then you can have any energy you want, but as long as you're bound to the hydrogen atom, you have to have one of particular energies. Okay, if you're in a stable place, and so if we look on the left, we'll see the different energy levels that become possible. So the lowest energy level is way down at the bottom on the left. It's in the first energy level, n equals 1. People generally call this energy level 1s. The 1 is the energy level, and the s is the shape. It's the particular orbital, which corresponds to one of these pictures over on the left. In fact, it's the one up near the very top and left that says 1, 0, 0 beside of it, and then you go up to the n equals 2 level. Okay, so for a given energy at the second energy level, if you're an electron with the energy that's in the second energy level that's possible, you could either have a little roundish orbit like the 2, 0, 0, or you could have orbits that look kind of like those next two. And by the way, this picture doesn't show all the possible orbits, because there's another set of two possibilities. There's another orbital possibility there too. If you go up to 3, you get even more. If you go up to the third energy level that's possible in a hydrogen atom, you can have that whole row of different orbitals that's that's pictured starting with 3, 0, 0, and things that look like those shapes. Okay, and this all comes out of the math, and these actual charge densities seem to be what we actually have in the atoms, and this stuff actually is going to explain all our chemistry and everything. So it gets a little harder. We can actually solve Schrodinger's equation for a hydrogen atom. When we have multi-electron atoms, the equation becomes too hard to solve exactly, but even then we can use computers that can do an excellent job of approximating, and they get out these very similar orbitals, but the energy levels become a little more difficult. Okay, because if I add an electron to a nucleus with a positive charge, I get one set of orbitals. But now when I add the second electron, okay, then it's also going to be affected by the first, and now the first one's going to be affected by the second. Okay, so it's not just the central nucleus in the center with a positive charge that determines the potential energy of an electron in that atom, but now it's also where the other electrons are associated. So what happens then is, it's interesting. You still have energy levels that are possible, but then the individual orbitals at a given, there's something called the primary quantum number, which is this n thing. But then, depending on the shape of the orbital, you can get slightly different energy levels once you have multi-electron atoms. And so, the lowest energy level is still 1 with the s orbital, then 2s. But then, and then 2p, but then you go up to 3s, but then watch what happens, then 3p, and then 4s, but then back to 3d, and so you get kind of a mixture going on. And I'll explain that better in just a second, I hope. But a couple of other things we have to bring into the discussion. You know, all the way back to the Bohr atom, Bohr built his whole model on the fact that you had quantized angular momentum. These guys, Stern and Gerlach, went out to find it. They were actually looking to disprove it because it sounded nuts to them, and they actually found it. Okay. Now, what they found was consistent with Bohr. It was also consistent with Schrodinger. Okay. Of course, now Bohr pretty quickly got replaced by Schrodinger equation, but the thing about the Schrodinger equation is eventually there were some similar experiments that were done, as Stern and Gerlach first did with silver atoms, that were inconsistent with the Schrodinger equation. Okay, and it would turn out that something else had to be going there, and so eventually it was noticed that even if you took a single proton and you ran it through this experiment, that you would find that the proton itself had a magnetic moment. So one thing the Schrodinger equation in its potential function had not accounted for was the possibility that the charge was spinning or not. So eventually it was found that these little charges, these protons and electrons, and neutrons for that matter, although they're neutral, they do have what's called an intrinsic spin, which means they have a little bit of a magnetism about them, which affects their energies. So that's going to factor into what I'm about to say in a second, but we need another stop before then. We have an observation sometime before all this in physics that shows that that the spectrum that you see of light when you like excite a material, like with an electric arc or something, that spectrum is different when you're in a magnetic field versus not. Okay, and so the reason turns out to have everything to do with these orbitals and also the spin of the particles. Okay. It also allows another physicist named Pauli, who's kind of an important guy in the history of quantum mechanics, to infer that that the way electrons populate an atom, as you add electrons to an atom, or you have atoms that have multiple electrons, apparently they can't just share these orbitals. They all have to go into their own place. Okay, there was evidence that they would always distribute themselves to the different orbitals. They wouldn't share these orbitals. Okay, and he called that the Pauli exclusion principle, and it turned out to be a very general principle. So whenever you have a particle with spin with spin in a certain unit, okay, and this all eventually comes out of the math, because right now it's an observation, but later it comes out of the math. When you have those sorts of particles, they can't share all the same. Their quantum waves can't exist in the same place with the same properties. Okay, it just can't happen. Which brings us to why it couldn't happen. There was a guy named Dirac, and Schrodinger did not do anything to make sure that his equation agreed with Einstein's special relativity. Dirac decided to adjust the equation so that it would also deal with special relativity. And when he did that, He was able to predict the Zeeman effect. He was able to show that the spin is automatically what would happen with electrons and protons and neutrons. He was able to, he was able to find those spins, or at least for protons and electrons. He was able to find the mathematical reason for the Pauli exclusion principle. Okay, and so it would seem that all is good here, by just taking the wave equation and kind of, which itself was energy conservation plus de Broglie's work, by also adding in Einstein's special relativity, the new wave equation would predict all these things, okay, which is great. We're going to use those ideas in a second. But interestingly, it predicted one more thing. All these particles like electrons, it also found that there's absolutely no reason why you shouldn't have particles just like the electron, but with a positive charge instead of a negative charge, or just like a proton, but with a negative charge instead of a positive charge. So whatever the particle was, same mass, same behavior, same spin, but the opposite charge. And at first, he just thought those were not meaningful, but later on, it was found that these particles really did exist. So the first example of these was called a positron. Now we call these things antimatter, because if you bring a positron and electron together, they annihilate each other, and they give off they give off high energy photons that add up in energy to what the masses were that came together. If you bring antimatter, if you bring protons together with their antimatter counterpart, they annihilate. If you bring whole chunks of matter and antimatter together, because you could conceivably have antimatter atoms, and in fact they've been created now, if you bring those together, you get total annihilation, total immediate, almost immediate conversion into energy. So that came out of the Dirac equation. Pretty amazing that math would predict such a thing. It was the positron was the first one found in 1932, and it was found in a cloud chamber. Okay, I think they were looking at cosmic rays, and they found positrons. Of course, antimatter is a favorite fuel of science fiction. We're not quite there yet, but we are here. This just happened this year. For the first time this year, they shipped antimatter from CERN to another location, and it was kind of a big press day, and they had the antimatter truck and everything out there, and they had the antimatter especially confined in magnetic fields and everything so that it would travel. But yeah, it's kind of interesting. So I digress, back to trying to get to proper quantum mechanical explanation of the atom. We need one more thing to kind of get to the big story. Finally, the thing that we get to, another scientist named Hun came up with this rule. He figured out that if you added electrons to an atom's nucleus, as you add the electrons, when you do have multiple orbitals they could go in within a given energy level, they tend to distribute themselves first, okay, before adding into others. So thing is, your electrons they fill in they go to the lowest energy first, and then within that they try to spread out from the other electrons, and when they do spread out, their spins tend to align in the same direction, because that's more favorable in terms of energy. And so given this last principle, we can now fully describe the arrangement of the elements in the periodic table. So if we look at the periodic table and we look at the energy levels that are possible for these different shaped orbitals coming out of the Schrodinger equation, or actually the Dirac equation, now we can just take our electrons and fill them in. And basically the principle is lowest energy to highest energy, always. And then if you have multiple electrons going into the same exact energy level, they try to distribute to the different orbitals first, and then they try to and they try to do it in such a way that their spin is lined up the same way. Okay, so if you start with hydrogen, and we're talking about the lowest energy state of each of these atoms now, because it's possible for an electron to get excited and go to a higher energy level than it normally would be at. But your first electron goes into the 1s, okay, because it's the lowest energy level. When you get to helium, you have a second electron. It also goes into the 1s orbital, because there's another space open, because you can have the electron can be spinning in the opposite way, so it can't have all the same quantum values. The first electron that went in has a spin that's we'll say it's either up or down, and the helium, the second electron comes in, and it's going to be the opposite spin, so they can both fit in the 1s, but no more electrons can fit into the 1s. Okay, so if you have any more electrons, they could not go into 1s without duplicating the exact same state as one of the two electrons already there, and that's not allowed by the exclusion principle. So let's go to lithium. It has a third electron. Where does it go? Well, it can't go to the 1s. The next highest energy level will be 2s. Okay, and so go to beryllium. The next highest energy level would be well, you could fit another one in 2s, but have the spin pointed down. And then you go to boron through neon, and you'd find yourself going into the 2p level. Okay, first you would go, boron, carbon, nitrogen. You would go individually into three different orbitals that were kind of oriented differently, and then you would fill in with your electrons with the opposite spin in the opposite direction, and get yourself to neon and have a complete second shell. And then you see that you would go to 3s. So 2 will go into 3s, and then you could have. But here's what I want you to see. The first row of the periodic table has 2 electrons. Look at that 1s level. It has room for 2 electrons. The second energy level in the periodic table, it has room for 8. Or there are 8 elements there. Look at how much room we have in the second level there. We have room for 2 electrons in the 2s, and we have 3 2p orbitals, like different orientations, and 2 electrons can go in each of them. That's a total of 8. Okay, now we look at the third row. Okay, so we have 2 electrons that can go into 3s. We have 6 that can go into 3p, just like the second row. But then, before we can put any more electrons in the third level, the 4s level is actually lower than the 3d level. Okay, so we actually end up filling in potassium and calcium, right, with the next electrons on the it's part of the fourth shell, but they're slightly lower energy now than the 3d electrons. But after you do the 4s, 3d is next, so you go back into the third shell and you do scandium through zinc. What I'm trying to say is this completely explains, coming out of this crazy Schrodinger equation with the relativistic twist that directed, this completely gives us back out the shape of the periodic table, the exact arrangement. Okay, so that's pretty amazing. And we could figure out what the electron configuration of all the elements is. So here's an example of a periodic table where someone's done it. Okay, it's actually pretty easy to do. It's something that typically people learn in their first chemistry class in college, sometimes even in high school. This is taught. So what is this all about? Yeah, we're ready to explain magnets. We're finally ready to explain magnets. Because of the way electrons fill in these orbitals, you end up getting electrons populating like the d orbitals, the 3d orbitals for iron, cobalt, and nickel. They're called ferromagnetic elements. They make good permanent magnets. You get the electrons going into there. Now the d level actually has enough room for 12 electrons total, but the first so many will each go into their own d level orbital, and they will have their spins going in the same direction. Now the little spinning charges, even Maxwell's equation would tell us that those act like little magnets, and they do. And so the fact that they're all lined up means that these atoms, iron, cobalt, and nickel, ending in each individual atom is like a little magnet, because the little electrons, which are magnets, are all lined up just so that the magnetism adds together from all of them. And so if you have a metal where the atoms have been subject to a magnetic field so that they tend to line up, you have a permanent magnet now. And that's how magnetism actually works. This is just a picture of what we talked about for iron. You see in the 3D, iron has, I'm sorry, there's room for 10 electrons there. It has 6, so it has 5 all pointing up, and then it has 1 down electron. But it's those, all those up electrons that aren't offset by a down electron that give the individual iron atoms their magnetic property. Okay, real quickly, we've spent a lot of time talking about quantum mechanics as something that applies to atoms, but it also applies to molecules. So starting at about the same period of time, you have an American scientist named Imes, who started actually studying molecules, multiple atoms bound together using infrared spectroscopy. And so he was able to show that quantum mechanics applied just as well to electrons that were part of molecular bonds and active and were active in chemistry, as well as molecular rotations and vibrations and that kind of thing, which were quantized. He made a tremendous contribution. He showed that quantum mechanics actually govern not only the world of atoms, but also the world of molecules. And he came up with some very refined techniques to do better and better spectroscopy, which enabled still more discoveries because it's always been just a major tool. And at this point, enormous strides begin to happen pretty much in every aspect of chemistry, the understanding of chemical reactions and crystallization and material properties, and all predicted or consistent with quantum mechanics. There are a lot of things that were predicted by quantum mechanics that would never have been looked for, and they seem strange, and yet they were found to be there. Well, it's taken about 100 years for a lot of the ideas in quantum mechanics to really take root and develop. Some of them happen very quickly, and then over time, a lot of things benefited from them, like chemistry, electronics, all kinds of things. But today, we find ourselves in the middle of what I think is a second quantum revolution. It turns out there's an important property in quantum mechanics, or current idea in an important idea in quantum mechanics called entanglement. Originally, Einstein and a couple other guys wrote this paper about it, kind of like the Schrodinger's cat example. They were trying to show that there was some part of quantum mechanics that still was just absurd. There had to be something else. That's what they were hoping to show with that paper. And let me give a simplistic example of what entanglement is. Let's say somehow you have two matched socks. Okay, you buy them from the store, so you have a right sock and a left sock. Let's say they're different. Okay, let's say they're fancy socks, and there's a right foot sock or a left foot, or maybe we'll say shoes. You buy a pair of shoes, so you have a right foot and a left foot. Now, let's say you put the shoes in a drum, and you shake the drum and everything, move the shoes around, and then without looking, you reach down in the drum and you pick out a shoe and you put it in a box, okay, and close the box, and then you take the other shoe out and put it in a second box and you close it without looking, and then you send the two boxes, each with one shoe, in the opposite direction. Let's say one goes 100. Let's say one goes to Mars and the other goes to Venus. Okay. All right. You know that there's one right shoe and one left shoe. So when someone opens the shoebox on Mars, immediately you can tell which shoe you have on Venus, right? It's going to be the other one. So if the right foot shoe is on Mars, then the left foot shoe must be on Venus. We say that their values are entangled because what the property that each shoe has that's kind of entangled here is its footedness, maybe, whether it's a left or a right shoe. It's handedness. I guess since left hand, right hand, but those two are related. So you kind of have either possibility until you open the box, right? But when one or the other person opens the box, whether it's the person on Mars or on Venus, you not only do you know what shoe you have, but you know what shoe the other person has. Okay, because of the entangled nature of the properties. Now, Einstein, was trying to use this sort of example with quantum mechanics, but he was trying to add the quantum weirdness in, because, in quantum mechanics, if we treated the shoes quantum mechanically, we would say that each shoe was not a right shoe or left shoe, but each shoe was in a superposition, a combination of right shoe and left shoe states that would not be determined until you looked in the box. Okay, and so Einstein was saying that the very instant someone looked in the shoebox on Mars, it would cause a collapse of the wave function and would cause the state of the wave function to resolve into whether or not you had a right shoe or left shoe, and immediately, instantaneously, faster than the speed of light, you would know what the shoe on Venus was. In other words, and anyone in Venus who happened to look at that, 1 microsecond or one fraction of a microsecond after the person on Mars looked, would see the shoe that had to be seen to be consistent with having both a right-hand shoe and a left-hand shoe. But the point is, because it's quantum mechanics, until someone looks in one of the boxes, you don't have a right hand or a left hand shoe. You have a superposition of both possibilities in each box. Okay, that's what quantum mechanics says. And to Einstein, that was ridiculous, because that meant that resolving the wave function in one place instantaneously faster than the speed of light could communicate the result had to cause a collapse of the wave function in the other location. And so this quantum entanglement, as he called it, was supposed to be an illustration of why it is that there had to be something more in quantum mechanics, because his ideas from relativity were increasingly thought to be an important aspect to what we call causality at a deep level. And so they would kind of violate causality in so much as the information would the change the wave function would travel faster excuse me, than the speed of light. Okay, many years later, okay, John Bell conceived of a math test to do an experiment, and that would allow an experiment to be done to test the conjecture that Einstein, Podolsky, and Rosen had put forward in their paper, which is called the EPR paradox, because they're first letter of each of their last names. And based on John Bell's work, an experimentalist named John Clauser found indeed the entanglement happens, and it really does work that way for quantum typically these are electrons or photons or something, not socks or shoes, but it turns out that this property, this entanglement property, is essential for the current revolution that's going on in quantum mechanics. They're working very, very hard, and they've got simple ones already. But they're working very, very hard on practical quantum computers, which for some sorts of tasks are going to be as much more powerful, are going to be as much more powerful than our computers today, as our computers today are compared to an abacus that can do like addition. Okay, I mean, and that's an understatement. It's really amazing how the ideas of quantum mechanics can be exploited to achieve these things called qubits, which can kind of take on all the possibilities at once, and you can kind of do all the, you can kind of do a lot of, if effectively you can do simultaneously all the possible calculations at once to see which one is right, and that's a big deal. The other thing is quantum sensing. They're using entanglement. It's possible to get around limits in optics so that you can actually see things better than you would expect from the traditional rules of optics in classical physics. I mean, there are no end of examples of things called quantum sensing, where you can have sensors that can tell you things that we couldn't do any other way. Okay. Now, all of these things are based on John Bell's work, and yet, there's no assumption of any. I mean, all of this stuff is based on John Bell's work. None of it is local in the sense that we were talking before. In other words, things are happening now that cause a difference across vast differences faster than the speed of light. So it kind of violates this locality condition. But it's been demonstrated that this really is what happens. The 2022 Nobel Prize was awarded for showing that in this sense, the universe is not, quote, locally real. In other words, that entanglement seems to have the possibility of affecting things, across vast distances, no arbitrarily large distances, and there's just no way to say that only things that are local affect the things that you're measuring. Sorry, I dropped something. Okay. Moving on. Oh, before we move on, pilot waves. So we talked about how pilot waves violated uh, locality, conditions of locality, and so apparently quantum mechanics, even without pilot waves, violates this long cherished condition that only things that are very local can affect a particular thing that's happening in a particular moment. Pilot waves aren't ruled out either. By the way, there is a proof in quantum mechanics that says you cannot have local hidden variables. You can have non-local hidden variables. In other words, hidden information that's global. And so that's why pilot waves are forced into that. Okay, but quantum mechanics is, with the idea of entanglement, has taken us in that direction. Okay, so all that to say, quantum mechanics is weird, but it's given us so many advancements and everything, and yeah, we're still wrestling with it. But putting all that aside, even maybe to the extent we're not putting aside, but embracing it as something that God created. That's the way He built reality. I think we can talk just perhaps about the miracle of quantum mechanics. What if classical physics was right and there was strict determinism? You know, if you follow that to its consequences, that idea to its consequences, there would be no chance for anything random to ever occur. But not only that, there would be no mechanism for anyone to have any real choice or free will, because it would all be, the deck would already be stacked. It's like, all your brains, everyone's brains full of neurons would all be in a particular state that would enable the prediction of the next state they would be in. So if you take a materialist worldview, a strict determinism like in classical physics, it would turn us all into robots. On the other hand, suppose everything is truly random, not just probabilistic, but random. That seems pretty impersonal. If everything happens pretty much randomly, it pretty much takes away from anyone's personal agency. Doesn't seem like there could be much in the way of fairness there. So on the left, I refer to Ecclesiastes 9:11. The race is not to the swift, or the battle to the strong, nor does food come to the wise, or wealth to the brilliant, or favor to the learned, but time and chance happen to them all. Okay, it sounds like outcomes depend a lot on a sort of chance. That means, hey, we don't seem to have any control, and nor are our actions tied to their consequences. If you've got complete randomness, then that's not necessarily a happy place to be either. Okay, but probabilities leave the possibility of empowerment and freedom available. Okay, so if you have possibilities, then that seems to be more compatible with the idea of choice or free will, right? You have possibilities. You have freedom if there are possibilities to choose between. So I'm reminded of the verse in Galatians chapter 5 verse 1. It says, "It is for freedom that Christ has set us free." And this is maybe the main point of all our philosophizing earlier on for me. Many great physicists have looked at quantum mechanics and thought that if it's so, God plays dice with the universe, which is why Einstein didn't like quantum mechanics. But may I suggest that we have reason to believe that it's not so much that God plays dice with the universe. In other words, that God's employing just randomness to determine which possibility resolves. But in some ways, God is the unseen dice. In other words, God himself determines. And for that, I would like to look at Proverbs 16:33, the last verse on the left there, and this was our key verse. The lot is cast into the lap, but its every decision is from the Lord. What this verse says, tucked away in Proverbs chapter 16, is that God is absolutely sovereign over every outcome that ever occurs. What to us seems probability um, is just an aspect of God's sovereignty as to which choice actually, or as to which possibility actually unfolds. So God can determine the possibilities to whatever extent God wants to. In some ways, that would make God, in the language of quantum mechanics or theory about quantum mechanics, that would make God the ultimate non-local invariable. So God's sovereign choices would determine the outcomes. And it seems to be very suggested in Proverbs 16, verse 33. That's how it is. So in my mind, God reigns sovereign over endless possibilities with mercy, grace, and loving kindness in a way that's compatible with the free wills that he gave all of us to choose to love him back for his great love. Okay, so that brings us to the end of the material, and thanks for listening, and I hope you follow through on the next. All right, have a good night.